In mathematical analysis, we rely on sequences to locate exact values. Sometimes a sequence behaves predictably and firmly anchors to a specific destination point. Other times, a sequence that appears perfectly stable will suddenly vanish into a gap that, intuitively, shouldn't exist. This is a table of contents from James Munkres' authoritative text, Topology. Chapter 7 is dedicated entirely to a concept called complete metric spaces. This mathematical framework explains exactly why those gaps exist and how to prove a space is free of them. For students facing advanced examinations like the CSIR NET, GATE, or IIT JAM, grasping this concept is non-negotiable. It is a relentlessly tested pillar of higher mathematics. If a space lacks the guarantee of completeness, the theoretical foundations of calculus break down. We lose the ability to trust that limits actually exist within the space we're analyzing. To understand completeness, we first have to separate pure topology from mathematical analysis. Topology is flexible. It focuses on open sets, continuity, and how spaces behave under elastic stretching. Analysis is rigid. Analysis requires a formal metric space. This is a set of points, x, paired with a strict distance function, d. It provides an unforgiving environment where the physical distance between any two points can be precisely measured. Completeness relies entirely on that specific distance function. It is a property of the metric itself, rather than the underlying set of points. To evaluate a space for completeness, we must temporarily abandon topological flexibility. We have to rigorously define what it means for elements in a sequence to get definitively close to one another, without assuming their final destination actually exists. Normally, a sequence converges if points march toward a pre-existing target, staying within its epsilon radius. But if testing the space itself, that target might not exist, and the test fails. The Cauchy sequence solves this, as elements target each other instead of a fixed point. The formal rule states that for any epsilon, there is an index threshold, where the distance between any two subsequent points becomes arbitrarily small. They pack infinitely close together. This gives us an absolute operational rule. All conventionally convergent sequences are Cauchy sequences. However, not all Cauchy sequences converge. Checking if a sequence is Cauchy reveals if the sequence wants to converge. If it is Cauchy but fails to hit a limit, we know the mathematical space lacks the structural integrity to catch it. This brings us to the formal definition. A metric space is strictly complete if and only if every Cauchy sequence within it successfully converges to a limit point existing inside that exact space. The real number line under the standard Euclidean metric is the ultimate complete space. It is a seamless continuum with zero missing values. Zoom in on the rational numbers, and the seemingly solid line is riddled with empty spaces. A sequence like 1 + 1 over n to the n tightly clusters, making it Cauchy, but its limit is Euler's number, e. Since e is irrational, the sequence falls through a literal hole. The rational numbers form an incomplete space. They host perfectly valid, tightly packed Cauchy sequences that simply have no valid destination point within the borders of the space. Munkres' topology provides tools to test for this structural integrity.
Theorem 43.1 states that a metric space is complete if and only if every Cauchy sequence has a convergent subsequence. The forward logic is straightforward. If the space is complete, the main Cauchy sequence converges. By definition, any smaller sequence extracted from it will identically converge to that same limit. The reverse logic is a powerful tool. Assume our main sequence is Cauchy, but we only know its glowing subsequence hits a specific target point, x. Applying the triangle inequality, the tightly packed main sequence is physically dragged to x by the convergent subsequence. This theorem gives us a powerful operational shortcut. If you can prove that just one subsequence converges, you instantly anchor the entire Cauchy sequence and establish completeness. We also need rules for when a smaller portion of a complete space, a subspace, is itself considered complete. Theorem 43.2 states, let X be a complete metric space. Subspace Y is complete if and only if Y is a closed set in X. If the subspace Y is complete, any convergent sequence within it must have a limit that exists inside Y. This perfectly matches the topological definition of a closed set, a set that contains all of its limit points. Assume subspace Y is closed, and we drop a Cauchy sequence inside. Because overarching space X is complete, the sequence hits a limit point, L. Since Y is closed, it inherently contains its limit points, securely trapping L inside, proving Y is complete. Closedness acts as the exact topological counterpart to the metric property of completeness, allowing the trait to be successfully passed down to subspaces. This brings us to a massive, exam-failing misconception. Many students assume completeness is a topological invariant, a property that survives continuous transformations. It is not. A homeomorphism is a mathematical mapping that continuously stretches and bends a space, flawlessly preserving open sets and general topology. However, homeomorphisms can completely destroy metric completeness. Let's map the open interval from 0 to 1 onto the entire real number line. The open interval 0, 1 is incomplete. The Cauchy sequence 1 over n tries to converge to 0, but 0 is excluded from the open set. We can map this incomplete interval to the complete real number line using a mapping function. As the mapping stretches the short segment outward infinitely to match the real line, the once tightly packed Cauchy sequence points are pulled infinitely far apart. We have established 3 core rules. Cauchy sequences indicate tight relative packing, completeness requires 0 gaps in the metric, and closed subspaces safely inherit this completeness. These rules scale up. In advanced mathematics, we move from studying points on a line to studying entire spaces of functions. Ensuring your target space is complete is the absolute only way to guarantee that sequences of functions converge into a stable, predictable function. This strict requirement births the concept of Banach spaces. When faced with a topology problem on an exam, always interrogate the specific metric before assuming a space is complete. Metric spaces may seem abstract, but checking for completeness is how mathematicians prove that the ground beneath their equations is solid. It is the gapless foundation required for all modern analysis.